Today we're going to review an example of an eVTOL powertrain using ePOP. What I've loaded in, imported in is the hover functionality for the eVTOL. It's a pretty simple power cycle, the takeoff and landing. The change here is the customer has a battery-only version of this eVTOL that is able to do this power cycle for 15 minutes, and now they want to extend it to 30 minutes. The optimization problem is, what is the best powertrain given this extension of duration? Is it still batteries, or does a combustion engine make sense at this point? So let's move to the configuration. Here's the configuration. It's basically a series, a plug-in series electric to complete the hover function. So the power could come from the batteries, could come from the genset, which is represented here. And the technology of each of these icons is represented over here on the left. Each one of the icons has a technology definition. Now, for this aerospace application, the genset, the engine, generator, and the rectifier come as a defined package together. So I've actually defined it all in the engine, and then I've made the generator and the rectifier simply pass-throughs, because all the efficiency of the component definitions is going to be defined here at the ICE. Now, this is the configuration for the eVTOL, and we have the ability to have both an A and a B configuration. Right now they're on top of each other. This genset, I have it defined both as a technology which can be scaled infinitely up or down, but in reality there are actual components that are available in the market. And in this case, under ICE, there's the technology, generic technology, but then there's the actual component. And the difference is the actual component has a power that's associated with it. I gave it a small range. Basically, it's at 40 kilowatts. You can buy this particular genset. But what I'm going to do for Powertrain B is I'm going to select the actual. Now you notice some changes here in the electrification percentage. What this is showing is this configuration and technology that you see, but it's applying the solution, solving for all possible powertrain options between 0 battery and 100%. So battery only and everything in between. And once I selected that actual, you actually see some variation. The solution changes when you constrain it to the actual component. What you're seeing here is mass, total mass of the powertrain. But there are other KPIs, cost and volume among them, that you might be optimizing and want to optimize and look at. So we've got some interesting results. So let's go to the results page. So in this case, Powertrain A is the BEV only, right here, the BEV only option. And Powertrain B is using the actual aerospace genset. And it could be any of these solutions, but this is decreasing the amount of batteries. But then, because of the limitation, the engine can't get any larger than this. This is the minimum amount of battery that can be applied with that genset to achieve the same power cycle that was defined in the application. So the power cycle in the application with the configuration that we saw, what we're looking at is all the options between the BEV only and this actual genset. You can see, we want to see the mass. We're able to decrease the battery by this much by adding the genset. This is the genset mass impact for this net. In this case, a 54% reduction in mass for this powertrain. Now, there are other volume has a similar impact. So by going to this genset, you are reducing volume of the powertrain. Let's look at the cost. This is total cost of ownership. Total cost of ownership increases slightly because you're going basically from cheaper electricity to more of your operational cost is coming from the fuel. So that's the background of what's being calculated by the total cost of ownership. The fuel cost goes up. You're going to save on electricity, but your fuel cost is going to go up, and that's what nets the increase. How much does it increase? Well, you can see there. If we go back to our mass, what is the makeup of two solutions? Well, this is what the battery only solution looks like. And when we take the genset and minimize the battery as much as we can, this is the powertrain mass. You can see the makeup of what the ICE, which is really the whole genset, is included in this powertrain. So a lot of information here, able to go from a 26 kilowatt hour pack to a 4.5 hour kilowatt pack. If you kept going, you could see there's diminishing returns. Actually, the mass would start going up if you were able to increase the size of the engine. So this is actually very close to the sweet spot in mass optimization for this 30-minute duration cycle.